We're going to be talking about the concept today of embedded systems. What it is an embedded system exactly. And you kind of get the sense we're going to be using something called an Arduino Uno. And okay, so what is all this stuff? How do we use this stuff? Where are we going with it? What's the purpose? All of these things we introduce here in this lecture today. So, in terms of our class, we have these 4 objectives that we want you to be able to do at the conclusion of this class. Basically, in this class, we want to give you mad skills. That's the bottom line. And these are the mad skills we want to give you. First, we want you to be able to interface a microcontroller to a variety of analog and digital inputs and output devices. Second, we want you to be able to implement a closed-loop automatic control system using a microcontroller. Third, we want you to be able to write and troubleshoot assembly language code for a microcontroller. So, assembly language is an important aspect of this class because it allows you to get down to the bare, essential functional components of the system. And finally, to analyze a problem to determine appropriate microcontroller use. So these are the learning objectives for this class. Mad skills. We want to give you these mad skills here in this class. There are going to be educational skills we're going to be having you learn, but there are also going to be practical hands-on skills. So there's a big component of this class is hands-on skill, but there is also, especially like with assembly language and such, it's going to be more technical. So hold on to your seatbelts or something, because we're going to go for a wild ride here in this class. Okay, in terms of the required acquisitions, here's the textbooks we're going to be using. You definitely need a copy of the textbook, okay, because it has certain tables and things like that, reference information that you will need that it's hard to find elsewhere, and I won't give you it, okay, because it's in the book. So these are recent prices for these things. So compared to a lot of classes, it's pretty cheap. Okay. So that's the book. You can find it at the bookstore, or if you can get it online, or at A-Books, or COAS, or wherever else you can find it, you definitely need to get a copy of this. So we're going to be using the Arduino, and there have been some available in the office. It's questionable as to whether they'll be available, and I'm still not sure if they'll be available or not. You can get them online, and so I recommend you getting your own Arduino so that you can work with these things on your own and your own time, your own computer, because it's very helpful for you to be able to understand exactly how all this stuff works and to be able to make it, test it out. So that's the Arduino. The Arduino IDE, the Integrated Development Environment. The Integrated Development Environment is the programming environment for this. It's free on arduino.cc. So we're going to be using this, and actually here I say we're going to be using this at this date. Actually, we'll be using it even sooner than that. We're going to be using it to start programming right away with this, and definitely in the lab as soon as we can. Next, there's the EduShield. There's the EduShield, and so this EduShield is useful. It has a number of valuable things associated with it. It's got some push buttons on here. It's got a light sensor. It's got an RGB LED, and it's got some other LEDs. It's got a temperature sensor. It's got a infrared transmitter and receiver. It has a buzzer. This is like a rotary encoder. It's got a connection for a servo. So this gives you a number of capabilities for different things, inputs and outputs that can be used for testing things. So it's helpful. This is a book that's helpful to give ideas for projects, sensing and controlling the physical world with computers. So this is a helpful, recommended acquisition. So what exactly is an embedded system? Well, we're going to talk about that. In particular, generally involves integrating sensors, actuators, intelligence to produce a system that is more capable, more versatile, more robust, to give you, to take a system that you have and to do something more useful with it. Okay, so we have a system. When do we use it? When is it appropriate to use a microcontroller? Well, generally, as we mentioned, one of the things that embedded system uses involves intelligence. You want to be able to incorporate intelligence into the system. So, if you have a system that requires intelligence, then that's the kind of thing we want. So, if, for example, you want to you push a button and you want a light over here to flash 3 times, or rather to give out an SOS signal, long, 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 short, 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 long, 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 short, short, short. Okay, so one push of a button sets that up, and maybe if you push it again, it turns it off. Okay, so it could be a warning beacon or a help distress call. Okay, so one push of the button does all that. Okay, and so you can think of there being intelligence required in that. The complexity of the system. You may have a system and the complexity is reduced by using this. So it turns out that you can do that SOS kind of thing. You can set that up using switches and relays, timers. But if you were to use all of those things, it can be a fairly complicated system by the time the whole thing is said and done. Okay, so if you can reduce the complexity, so instead of having a bunch of relays and a bunch of switches and a bunch of timers, if you can do it more simply, another way, then in particular using a microcontroller, then it's good to do so. Cost can be an issue. The cost of the microcontroller can be less than other parts. Okay, it may be that you need a variety of sensors and actuators must be integrated in the system. Or perhaps communication. Some kind of communication is needed. Those are the kinds of things that would warrant using a microcontroller. Now, microcontroller isn't useful for everything, and there are times when it's not necessary to use one. It's not the correct tool. So, for example, if the system requires little or no intelligence. In other words, if all you want to do is turn this thing on, you flip a switch, this thing goes on, then you don't need a microcontroller for that. Perhaps the system can be simpler or cheaper using individual parts. Then you don't really need a microcontroller. Or the microcontroller might actually be, so in this case, the microcontroller is overkill. Or it could be that the microcontroller is underkill. In other words, it may be too slow, maybe there's too much number crunching involved, or there are too many things going on for the microcontroller to keep up with. The microcontroller can keep up with quite a bit, but it's possible for the microcontroller to be undersized. So there may be good use at times for a recommended use, other times not. Okay, here is the concept map for a embedded system. Okay, here's the concept map. So over here, we have this system that needs to be controlled. We'll talk a little bit about what that system might be. Okay, so there are sensors, signal conditioner, there's a couple of power sources, there's a user interface with the system. Here is the controller. The controller is going to be like a microcontroller. There's a power interface, an actuator associated with the system. So basically, here's where the intelligence is. The intelligence is generally put into the system in the form of software. Okay, so what does the system need in control? Well, can be a variety of things. It can be a mechanical system, electrical system, or an electromechanical system, a combination of the two. So often when we have a system that involves both electrical and mechanical, it's often referred to as a mechatronic system. Mechatronic. So that's a combination of the two words, mechanical and electronic. Suppose you could do it the other way, electronical. Well, anyway, mechatronic system. That's the standard name for electromechanical systems. Could be a biological system, thermodynamic, chemical, and so on and so forth. So as you can see, what we're talking about is very useful for many applications. So when we start talking about embedded systems, we're talking about something that can control all kinds of things. So in terms of a system needing control, we have the question, what's wrong with the system? In other words, well, maybe there's not anything physically wrong, but we want the system to do something. So for example, the clothing may not be wrong, but you might desire lights to flash on your clothing. You may have a tie and you want lights to flash on your tie. So there's nothing wrong with the tie, but the question is, there's something we would like to do with it other than just have it as a tie. And so part of the question is, what can we do with it? So that's the issue that we're looking at here. So again, electrical, mechanical, biological, all kinds of things could be used here. So just to give you an example, there's a product called SAWSTOP. And the purpose of this is as follows. We know that there are lots of table saws, and table saws can cut off fingers. Okay, I have a brother-in-law that happened to, I have a friend that happened to. So this is certainly a problem. There's a problem associated with table saws. That is, they're potentially dangerous. Okay, so powerful. So there are plenty of electric saws. We don't need more electric saws. We need safer saws. So the question is, how do we prevent saws from cutting off fingers? Well, it turns out that organic bodies, like fingers, are conductive and generally softer than wood. So they have different properties than wood. So how can we use that knowledge then to solve this problem? Okay, so the smart saw basically applies a small electrical signal to the blade. There is a sensor and a DSP that monitors the signal. When the blade contacts skin, or as in the picture, a hot dog, the signal in the blade changes. And this change then activates a safety system. So basically, obviously, if the blade is not contacting skin, there's no issue, there's no problem. Okay? It's only a problem when the blade contacts flesh. Okay? So when that happens, basically the sensor and the DSP quickly detect that. So the electrical communications and connections here happen really fast, okay? A lot faster than you can move your hand. So let's say your finger is getting into the blade. As soon as it just barely touches, the electrical properties change. It's picked up by the sensor and DSP, and its safety system is activated. When the safety system is activated, three things happen. First, an aluminum brake locks onto the blade. It's like a block of aluminum just grabs the blade. So even though the blade is spinning, it destroys that block of aluminum, but in the process, it stops the blade. And in the process, the momentum of the motor also causes the blade to swing out of the way. Okay, so if you've ever, and the third thing is it shuts the power to the motor off. So if you've ever used a table saw, when you hit the off button, the blade doesn't stop spinning. It takes about 30 seconds before the blade stops spinning. It has to wind down. It's got a lot of inertia. And so what happens then is when the aluminum brake locks onto the blade, it uses the momentum, the inertia, to swing the blade out of the way, so it's no longer touching the finger. Okay, and so that's the kind of situation that we're looking at. That's the application. So that's the problem. That's the approach. Okay, now how do we apply this in an embedded system? Okay, so over here's our saw blade. Okay, and there are lots of saw blades out there, lots of different kinds. So this particular saw blade has a sensor, and the sensor injects a signal onto the saw blade, and it also measures that signal. Okay, so it applies something, it measures something. The DSP then is constantly checking what's going on with all this. So again, when your finger is in contact with the blade, the sensor identifies through the DSP that a change has occurred, and that is communicated now to the controller. Okay. Otherwise, the controller drives the power interface. There's a power interface that takes, the power from the wall, which is 120 volts. It takes that and it applies it to the motor. So that's what's used to drive the blade. Okay. When it's told to shut down, this connection is broken, okay, or rather opened, and then this connection is applied, so the brake stops it. So basically, power is applied to either one or the other, not both at the same time. Okay, and so that's what the power interface does. And so this is an example of what's called a closed loop system. Okay, we saw in our learning objectives, one of the learning objectives is to be able to apply a microcontroller in a closed loop control system. This is an example of a closed loop control system. So notice we have this loop here. So this is a block diagram for that. We have a number of components in there. We have the sensor and signal conditioner. And again, that sensor is required for closed loop control. So now what is a system called if it uses no sensor? If it's not closed loop, then it's what? Open loop, right, open loop control. So, now, and there are lots of valuable open loop control systems. So closed loop isn't the only way to go. So the sensor and the signal conditioner measures important system variables. These measurements may be used in general, will require conditioning to be used by the microcontroller. So for example, if you have a sensor that, the Arduino, for example, has an analog input, but the analog input only takes positive voltage. So if you have a sensor that gives negative voltage values, then it can't be used by the Arduino directly. You have to do something with it first so that it no longer has negative values. So they have to be. So the signal has to be conditioned for use by the brain. So in general, the conditioning may involve a number of operations: scaling, offsetting, filtering, in order to be used. So in general, these are the kinds of things that are needed in order to have a sensor. And again, this also will require some kind of power associated with it. Now, in general, there may be a number of power sources. In that first block diagram I showed, I had two different power sources. Okay, you may have low-level required power, and you may have high-level required power. So you may require multiple voltage levels. So for example, if you look inside of a PC, you have a power supply with like several different kinds of voltages available. So, and that's because, the hard drive needs one kind of power, the fan requires a different power, and so forth. A number of different kinds of powers. So in general, you may need to supply power other than electrical power. You may need hydraulic power or pneumatic power. Okay, so that's a different kind of power. It may require high power and low power levels. For example, if you were driving a motor, excuse me, the motor might require 30 amps. Well, there's no way you're going to get 30 amps going through an Arduino. You do that, and you're going to fry your Arduino. So it may require a higher amount of power. So in that case, you have what's called a power interface. So the power interface may need to do power amplification. So your Arduino puts out plus 0 to 5 volt values, but that directly may not be useful for a motor. So, but anyway, you have some kind of power amplification, and often that will be in the form of current amplification. So the Arduino can put out milliamps of current, but a motor might require 30 amps. So there needs to be an increase from the milliamps up to the 30 amps. So the important thing is that the power interface is able to handle the power requirements demanded by the actuator. So one little Arduino may not be able to drive a bank of lights, for example. So you need something else that will be able to handle the power needed by the lights. Okay. The power interface, in many cases, will require analog, but the Arduino doesn't have an analog output. So we may need to use something called pulse width modulation, and we'll talk more about this. Pulse width modulation is a way of simulating an analog signal using a digital signal. So here's an example signal that we might want in an analog, and here is a pulse width modulated version of that signal. So basically, the pulse width modulation, it puts out pulses at a certain period. Every so many seconds, a new pulse. The width of the pulse is determined by the magnitude of the signal we want out. So notice for low values, we have the pulse width is very small. For high values, the width of the pulse, the on time versus the off time. The on time is large. Okay, so here's very small on time. Here's very long on time. And so we can simulate a changing voltage by modulating the width of the pulses, by adjusting the width of the pulses. So that's pulse width modulation. Anyway, that's a form that's used in some cases, especially like for motors or other things, for driving things. Notice this is a digital circuit, a digital signal, but it represents something that simulates an analog. Your actuator is some kind of an energy conversion device. So it converts power from one kind to the kind needed by the device that's being controlled. So, for example, if you have a motor that's, you have a mobile robot, and you've got wheels, and the wheels are turned by motors. Okay, so that motor is an actuator. Okay, it takes electrical current and gives you mechanical output. So motors, brakes, pumps, solenoids, linear actuators, a number of different kinds of actuators. Could be lights. Those are different kinds of actuators. Okay, so in general, that may be a part of your overall system. User interface. So you have a user, a human, that's interacting with this system, and the user may want to put in information into what's going on in the system. So the user interface then needs to take input commands from the user. It needs to be able to, say you want to enter in a number. Let's say you enter the number 10, and a light over here blinks 10 times. Okay, so that would be an example where you want to be able to put in information into the system. Or maybe your input comes in the form of a knob that you turn, and that does something, and the system detects that change, and it does something based on that. Okay, so number of ways of getting information in from the user. So this is an example of a user interface. This has a lot of user interface features, this thing. So it can take information from the user, and it can give information back to the user. Okay, and that information can be in the form of a GUI. So, for example, this has a GUI, graphical user interface. There's a graphics associated with this, and what's going on in the graphics then is somehow communicating to the user, and the user can interact with that graphics. So, for example, a screen with a mouse or an arrow. That's a graphical user interface. Or the output could be visual in the form of a meter, a numerical readout, some kind of a warning light or indicator, etc. So basically, the user interface takes whatever information the user is going to give, and it returns back to the user information that's useful to the user. That's the user interface. The controller hardware then can be of a number of forms. It can be a computer, a microcontroller. It may involve communication circuitry, interface circuitry. It may also involve some amount of analog processing. Okay, so the intelligence in the system is coded into the system. It doesn't appear by random chance. It needs to be intentionally put in, intelligently assigned to the system. And so for the Arduino, we'll have the Arduino IDE, which is very similar to C or C++. We will also have you be working with assembly language for higher speed functions. For highest speed functions, we would actually use something other than an Arduino. We would probably use an FPGA. Those would give us higher levels of speed. And there we would use something like VHDL as our language of choice. There are quite a few manufacturers of embedded systems. So here are just a few embedded system or microcontroller systems, and so this is something that's huge. Those of you who are familiar with the Y2K scare that happened just before the year 2000, there was a great concern that when the clock rolled over from one millennia to another, that was going to throw off all kinds of computer systems. It was going to shut down all the power, turn off all the water, all of our utilities. It was going to do all this horrible stuff to us, and right in the middle of winter. And so there was this huge scare. There were some people who were very concerned about this because of the proliferation of microcontrollers. There's so many different kinds of microcontrollers used in so many different places that most people are not even aware about. And some of those microcontrollers use time functions. And so the concern was that the time functions would barf when the calendar rolled over, and all this stuff like your automobile and your microwave oven and all this stuff is going to shut down because the microcontroller wouldn't know what to do when it rolled over. Well, it turned out that we're going to use microcontrollers, and very rarely do we actually need to know what the time is when we are using a microcontroller. We don't really care what time it is, and so it's not an issue. Okay, so, but that was a big scare. And that's because there are so many microcontrollers used in so many different areas. So many different companies make them, and they're used for different things. But they're very ubiquitous. They're everywhere. Why the Arduino? Why would we want to use the Arduino? I mean, there's so many other microcontrollers. Well, there are some other options. In fact, another good one is the Raspberry Pi. That's an up-and-coming one. There's also different versions of Arduino. There's the Uno, which is very important. There's the Due, which is more powerful. And then there's the Arduino Yun, which is like really powerful. It's almost like a single board computer. It'll run Linux and all that. So there are different Arduinos. Why the Arduino that we're using? Well, first of all, here's some of the reasons. Improvement over other microcontrollers for hobby usage. So the key here is it's for hobby usage. That is, it's designed to be used by people who are artists, not technical people. Okay, and so it had to be simple and yet powerful. So that's important. It's inexpensive. It's really small, cheap. It's really nice. It has an IDE on multiple platforms, Mac, PC, Linux. So anyone with a personal computer can, or a small computer, their own computer, can design software for this thing. So remember, the software is where the intelligence comes in. So it's pretty important to be able to do that. The programming environment is similar to C. It's actually based on something called wiring, which is based on C. And so it's very straightforward, very standard type of programming. It's open source and extensible, both software and hardware. And there are Arduino shields. It's these two things that really make the Arduino powerful. Okay. So first of all, software-wise, there are oodles and oodles of libraries that people have worked hard at designing. So they've done the hard work so you don't have to. And you're going to use some of that. You're going to use some libraries, and you have no idea the complexity of what's going on behind that library. So it can be as simple as, it can be like communication. We're going to use a communication library that allows you to communicate serially from the Arduino to the computer console, so you can actually get a display readout. We're going to use a stepper motor library that allows you to control stepper motors. Stepper motors are pretty complicated. There's a lot of sequencing involved associated with the control of a stepper motor, but you're not going. It's going to be like invisible to you because it's just there. Someone has developed a library to do all of these functions that once were very complicated to do, and to have to do those things like micro-stepping of a stepper motor. Some of those things are really complicated. You don't have to worry about that. You can just use it, and that's really the power of this. Open source, extensible software and hardware. So the open hardware, we have what are called Arduino shields. These are like additional circuits you can add onto your Arduino. They just kind of like stack right onto your Arduino that allow additional capabilities of your system. Here are some example Arduino shields. You can get a camera, VGA camera, a GPS onto your system. LCD, you can get an LCD or LED displays. You can connect to the internet through Ethernet or Wi-Fi. You can control motors, as I said, like a stepper motor or a DC motor or a servo motor. You can have relays. They sell a mobile robot that works with the Arduino. Okay, accelerometers, gyroscopes, load cells. All of these things can be used with the Arduino. We have additional capabilities. There are MP3 players that go with an Arduino. Just so many things have been built. So you saw, for example, the Edu Shield that stacks on top of the Arduino that we'll be using. It has a number of capabilities: LEDs, push buttons, infrared transmitter receiver, so forth. All kinds of things are available. Here is an example Arduino application. This is just the connections, but this is an Arduino web server. So we can connect to the internet through Ethernet. So this is an Ethernet card. There's storage on here that actually will store the web pages and web data, like pictures and such. And then, of course, there's the processor, the Arduino itself. And so all of this together in a tiny little package can be used to create a web server. Before, this kind of thing was unheard of, to have a web server this small. But here we have it. Here we have it. We can create an Arduino web server. We can, for example, have a light dimmer. We have, say, a bank of spotlights we want to control. We want to control them based on the music. So we have over here the audio source that goes through some signal processing and high pass, band pass, and low pass filters. And those each are used by the Arduino to control these lights through relays. Okay, so here's an example of a lights being controlled like at a concert by music, responding to the music. Here is another interesting application called piano gloves, and I'll let the ladies speak for themselves about this.
That was bad. Hi, my name is Daniel Norman.
And my name's Chelsea Hancock.
And this is our version of piano gloves. And basically we used an Arduino Decimelia bare bones circuit board with a basic breadboard.
It's basically a bunch of push buttons on 2 gloves. And when you touch the thumbs to the fingers,
thumbs are positive
power, and then the fingers create a note when you touch it, just like a push button.
So it's just a bunch of push buttons basically. And the pennies on the gloves are normal notes, so that's a basic C scale. But the dimes are flats.
But there's also other dimes that control the octave changes.
Right here. So this is the left hand, and that's
the left hand controls the lower, whereas the right hand controls the higher. Good job.
Thanks.
So that's basically our project.
Yep. So thanks for watching.
So this is an introduction to embedded systems. We have shown you a number of aspects of the entire system. This is just kind of a big picture. When we come back next time, we're going to start getting into the nitty-gritty details. And when we get into the nitty-gritty details, we're actually going to get into them at 3 different levels. We're going to start off at the very high level. That's the level that the hobbyist sees. That is, you don't have to be extremely technical to be able to do that. There is some technical stuff that you still have to learn, but it's at the level that a hobbyist can learn. Okay. Then we're going to get down a little lower in complexity, rather higher in complexity. We're going to look down and we're going to actually look at the internal structure of the Arduino and be able to take advantage of some of the features of the Arduino that the IDE cannot handle. The IDE, the Arduino IDE, is limited. It can't access all the capabilities of the Arduino itself. So we want to be able to get down a little under the surface and be able to access some of those additional features. Then we're going to go even deeper into the system using assembly language. We're going to get down there in the assembly language, which is the lowest level, and we're going to see how to access things, and we're going to use the capability of the assembly language in order to handle things that are more speed critical. So that's the kind of thing we're going to be looking at. So those are the 3 levels we're going to be looking at, and that then is, all of this then is the overview or the introduction to this class and to embedded systems. Thanks for watching.